Today we discuss normal and self-adjoint operator. Okay, we write it here: normal and self-adjoint operator. Okay, normal and self-adjoint operator. So we're also going to discussion about that. Okay, that means we're first going to discussion one lemma related to these topics. Okay, so we write the statement of this lemma first here. Let T be a linear operator on a finite dimensional inner product phase V. Okay, if T has an eigenvector, so as T star. Understood? So we know about that. What? T be a linear operator on a finite dimensional inner product space, and T has an eigenvector, so as T star. Okay, understood? T be linear operator that means satisfies this operator means some space to space, and here finite dimensional means obviously basis contains finite number of vectors, and then inner product space means some inner product conditions are satisfied, and here that means V with some inner product, and T has an eigenvector, not a problem at all, so T star has an eigenvector. Understood? Now we're going to discussion proof. Yeah, proof, right? Suppose that okay, V is an eigenvector of T. V is an eigenvector of T. Okay, with corresponding eigenvalue lambda. With corresponding eigenvalue lambda. Understood? Then what happened? Then for any x belongs to V, okay, here 0 equal to 0x equal to what? Here V minus lambda I V x. Okay, so what happened is here this one V T difference lambda I star x. Okay, then this one equal to V here T star difference lambda conjugate I x. Understood? Inner product of this, and hence V is orthogonal to the range base of T star difference. So we write, so V is orthogonal to T star difference lambda conjugate I. Okay, so T star difference lambda conjugate I is not onto. Understood? And hence it's not 1 and hence is not 1. Okay, this one is, I think all are understand this. V is an eigenvector of T with corresponding eigenvalue lambda, and then for any x belongs to V, this one happen, then V is orthogonal to this one. Then this one is not on to what? Because T minus lambda I x equal to 0. Okay, that means we also get this one, this operator. If this operator is on to, then we also find what? That means every image have some pre-image. Okay, but here I think that means every image have some empty image, and obviously we also see that this one t star minus lambda conjugate I x equal to 0, and even this one is for any x. Okay, so this one contain that means scar of this equal to not equal to 0. Okay, so this one is not 1 1 and or not on 2 in this way. And again we also see that that means just v to v means x to then here we obviously here star lambda conjugate I x equal to what, 0. So not on 2. Understood? For any x this one happen, that means not on 2. Okay, so now we're going to further discussion of that. Then we erase that portion and going to further discussion of that. T star difference lambda conjugate I has a non-zero null space. Has a non-zero null space. Okay, and any non-zero vector in the null space, and any non-zero vector in the null space. Okay, any non-zero vector in the null space is an eigenvector of what, T star with corresponding eigenvalue lambda conjugate. Understood? That means here T star difference lambda conjugate I has non-zero null space. Okay, and any non-zero vector in the null space is an eigenvector of T star with corresponding eigenvalue, this one. Okay, not a problem at all. So what we get if T has an eigenvalue corresponding to an eigenvector, then we have done for T star. Understood? This one is too easily we done it. Now we're going to discussion one definition. Okay, what is here we write a subspace. Okay, a subspace W of V is said to be T invariant. Okay, if TW is contained in W. Understood? That means if W is T invariant, then TW x equal to Tx for any x belongs to W. Okay, so we write it here. If W is T invariant, okay, then the restriction TW, okay, here W to W by TWX equal to Tx for all x belongs to W. Okay, understood? Then TW is a linear operator, on W. Understood? That means is polynomial is said to be, again we write here, a polynomial is said to split. It's said to split if it factors into linear polynomial. Okay, Understood? Not a problem at all. Then we're also going to discuss another theorem related to that topics. Okay. Here one subspace W of V is said to be T invariant if TW is contained in W and W is T invariant, then the restriction TW is also a linear operator on W and its polynomial is said to split if it factors into linear polynomial. Understood? Now we're going to discussion of that. It is that portion. I'm going to further discussion of that. Here we write Schur theorem. Schur theorem. Let T be a linear operator on a finite dimensional inner product space. V. Okay. Then suppose that the characteristics polynomial is split. Okay. Then what happened? Then there exists an orthonormal basis. Okay, beta for V such that the matrix T with respect to beta is upper triangular. Okay, let T be a linear operator on a finite dimensional inner product space V. Suppose that the characteristics polynomial of T splits, then there exists an orthonormal basis beta for V such that the matrix T beta is upper triangular. Okay, then we're going to prove of that. The proof is by mathematical induction. On the dimension n of p. Okay, the result is immediate if n equal to 1. Okay, so suppose that the result is true for suppose that the result is true for linear operators on n-1 dimensional inner product spaces. Is true for linear operators on n-1 dimensional inner product spaces. whose characteristics polynomial split. Whose okay. So suppose that the result is true for linear operators on n minus one dimensional inner product spaces whose characteristics polynomial split. Now we're going to further discussion of that. Okay, so erase that portion. By the lemma, we can assume that state star has a unique eigenvector z. Suppose that this does z equal to lambda z and w equal to span of z. We saw that here w bar is t invariant. Okay, understood? Now if phi belongs to w bar, okay, and x equal to cz belongs to w, then what happen? Then inner product of dyx equal to here dyx equal to dycz, okay, equal to here y t star cz. Okay, here y c t star z equal to here y c lambda z. Okay, equal to what? Equal to c lambda conjugate yz equal to here c lambda conjugate 0 equal to 0. Understood? So if w belongs to y belongs to w bar and x belongs to cz, then this one happen. Okay, dyx inner product equal to 0. Okay, then what happens here? So dy belongs to w bar. Okay, now it is easy to show that what happened. Now it is easy to show that okay, the characteristics polynomial, the characteristic polynomial of t perpendicular if of t w perpendicular of r divides the characteristics polynomial of T. Characteristic polynomial of T. Okay, and hence split. Okay, and hence splits. Okay, now what happened is here. We erase that portion and going to further discussion of that. Now here we write by theorem dimension of W bar equal to n minus 1. Okay, now we may apply the induction hypothesis. We may apply the induction hypothesis. Okay, to TW path. Okay, and obtain an orthonormal basis and obtain an orthonormal basis. Okay, gamma of W bar. Okay, such that what? Such that TW bar with respect to gamma. Okay, is upper triangle by assumption. Okay, because if it has dimension less than n, and then we also do it. Okay, so next what happen is here. Next, then clearly beta equal to gamma union set. Okay, is an orthonormal basis. Okay, for V such that T beta is upper triangular. Okay, understood? So today we also discuss this theorem easily. Okay, by help of mathematical induction we also prove this one. Okay, then now going to discussion of some definition or discuss something. Now we write here. Okay, here we prove this one. So now we're going to discussion in this way: an orthonormal basis of eigenvector. An orthonormal basis of eigenvectors. Okay, of a linear operator T. Of a linear operator T. Okay, of a linear operator T on a finite dimensional inner product space V. On a finite dimensional inner product space V. Inner product space V. Understood? An orthonormal basis of eigenvectors of linear operator T on a finite dimensional inner product space V Okay, that means we have to find this one. We have to find this one. Okay, then what happens here? Then we also write it in this way. That means if such an orthonormal basis beta exists, we erase that portion, then we write it here. Okay, if such an orthonormal basis exists, okay, if such an orthonormal basis beta exists, if such an orthonormal basis beta exists, okay, then what happened? Then T beta is a diagonal matrix. Then T beta is a diagonal matrix. Okay. Then what happens here? We write it in this way: T star beta equal to T beta star. Okay. Hence, this one is also a diagonal matrix. Is also a diagonal matrix. Okay. Now, we also write it here. Diagonal matrix is commutative. Diagonal matrices commute. Matrices commute. Okay. We conclude that T and T star commute. Okay. Thus, if he possesses an orthonormal basis of eigenvector of T, thus if he possesses an orthonormal basis of vectors of T, then what happens? Then T star equal to T star T. Okay, understood. Now we erase that portion and going to discussion on definition. Okay. Let V be an inner product space and let T be a linear operator on V. Okay. Then we say that T is normal. Then we say that T is normal if T star equal to T star T. Okay. Here and n cross n here or complex matrix A is normal, or complex matrix A is normal if A is star equal to A star A. Okay, understood. Then we're also going to discussion this one. That means one operator normal, how this one satisfied, and one matrix normal when this one satisfied. Okay, now we'll also discuss here what T is normal if and only if beta is normal. Okay, beta is an orthonormal basis. Okay, understood. Now we're going to discuss another example here. We write it example related to that topics. Okay, so we erase that portion. Let t r square to r square be rotation by theta. Be rotation by theta, where 0 less than theta less than pi. The matrix representation of t in the standard order basis is given by in the standard order basis is given by a equal to cos theta minus sin theta cos theta. Okay, then what happened? Note that this star equal to what? Cos theta minus sin theta cos theta. Okay, then what happened? Then we write it a is star equal to I equal to a star I. Also think about that a is star. Here this one cos theta sin theta cos sin theta 0 sin theta plus 1. Yeah, a star cos sin 1 0 0 1. Done. Okay, so a and hence t is normal. So a normal and hence t normal. We erase that portion and going to discussion further. Okay, so we obviously start with another example. Suppose that A is a real skew symmetric matrix. A is a real skew symmetric matrix. Okay, then what happened? That is A transpose equal to minus A. Okay, then A is normal. Then A is normal. Okay, because both A is transpose and A transpose A and A transpose A are equal to minus A square. Okay, not a problem at all. Then what happens here? Then both are normal. Okay, but A is star and A star A equal to minus A square. Okay, so this one happens. So normal Understood? Now today we also stop here. If you get this type of video, please subscribe my channel. If you have any question, comment, suggestions, write it in comment box. If you want to give like, please click on like options. So thank you.